Hello, good evening, and I'd like to welcome everybody to the Royal Aeronautical Society for this evening's lecture, Explosives, the Past, Present and Future, with Professor Jackie Akhavan. My name is David Marsden. I'm the current chair of the Weapons Systems and Technology Group. I'm also a engineering manager at RAeS, but I'd like to introduce Jackie, and before we can get started on the lecture itself, there are a couple of housekeeping announcements I unfortunately have to make you aware of, as it were. So there will not be a fire alarm test in the building. If the fire alarm does sound, please exit the building, and the Society's designated assembly point is the paved and railed area at the junction of Hamilton Place and Piccadilly, beyond the Intercontinental Hotel. Society staff will be on hand to guide you. If you have any mobility or access issues, please make yourself known to a member of the event staff. They can make necessary arrangements for your safe exit in the case of any such emergency. Of course, please do not leave any unmarked bags or other items unattended in the course of the evening. And of course, can you please make sure that all mobile phones are switched off during the session. The event is being recorded and will be available on YouTube post-event. And after the presentation, there will be an opportunity for questions. So please raise your hand if you'd like to ask a question, and a member of the Society staff will bring a microphone. That bit is necessary for the recording that's being made, so could you please wait until you have the microphone before you ask said question. So, without further ado, Professor Akhavan joined the academic staff at Cranfield University in 1987 after graduating from Southampton University with a PhD in polymer chemistry. In the early 1990s, she was invited as a visiting research scientist to Akron University in Ohio to develop high-energy rocket propellant. In 2001, she was appointed Associate Dean of Undergraduate Studies, and in 2007, she was awarded a personal chair in explosive chemistry. And in 2011, she was appointed as a member of the council to the university, and in 2014 took up the position of Director of Education for Cranfield Defence and Security. Professor Akhavan has held a variety of positions external to the university, including member of the European Reference Network for Critical Infrastructure Protection, member of the National Industry Advisory Group for NATO on Demilitarisation, chairperson of the Wessex branch of the Association for Women in Science and Engineering, and has been a chartered chemist for over 30 years. She is the head of the Centre for Defence Chemistry and a member of the UK Defence Science Expert Committee, reporting to the Defence Chief Scientific Advisor to Defence as the UK expert in explosives and weapons systems. Her expertise is in explosive chemistry, and she has supervised over 20 PhD MSc students, written and contributed to 5 books, and published over 70 papers in peer-reviewed journals. The Centre for Defence Chemistry has state-of-the-art facilities for the manufacture and synthesis of novel explosives, together with an accredited test house for hazard testing and an explosives range at Kotek, where performance tests can be carried out. The centre also hosts the UK Centre of Excellence for Explosives. So without further ado, Professor Akhavan.
Thank you very much. First of all, thank you very much for inviting me here this evening, and see so many people actually turned up, which is really, really good. So it's worthwhile me being here and you being here as well. So I've got my pointer, and hopefully you'll know a bit more about explosives when you go home than you do now. So explosives, this is a video to show you where explosives can save lives. So, what is an explosion? And there's various different explosions. There's a physical, there's a nuclear, and there's a chemical. So a physical explosion, a good example is when you put some water inside a metal container, and then you heat the water up, and as the water starts to boil, the gases can't escape. So the pressure inside that metal container gets higher and higher, and eventually the metal container will burst, and you'll hear a large bang, and as the water goes from a liquid to a vapor very, very quickly, and that's a good example of a physical explosion. Another good example of a physical, the largest physical explosion this planet has seen is when the Krakatoa volcano, which is on the Krakatoa Island in the Indian Sea, it evaporated. And as this volcano evaporated, the lava fell into the sea and set up a tsunami. As the tsunami went for 200 miles, all these islands, in the Indonesian islands, the people obviously drowned. And when they went back to have a look what happened, the people were burnt. And all the vegetation were burnt just one side, and all the people just one side were burnt. But they were drowned as well. And I thought, how is it possible you can be burnt but drowned at the same time? So the theory goes that when this lava fell into the sea evaporated, and it evaporated so quickly that as it went from a liquid to a gas, to a vapor, it squashed the air and sent a shockwave across the sea. And this shockwave had very hot gases, talking about 3,000 to 4,000 degrees centigrade. As it went across the sea, it hit the islanders. So every islander or vegetation that the shockwave hit, it burnt them. And unfortunately, then the tsunami followed afterwards. And that's a physical explosion, so the biggest so far on this planet. That happened last century. A nuclear explosion, of course, is the most powerful explosion. It has huge amounts of energy, gamma rays, infrared rays, high pressure, positive pressure, negative pressure, and that's the most powerful type of explosion. I'm talking about today chemical explosions. So the definition you can see is what a NATO definition, or sorry, UN definition of an explosion actually is. And just to give you sort of the red bits highlights, an explosive substance, it can be a solid, it can be a liquid, and it undergoes a simple chemical reaction. That's all it does. And this chemical reaction, the products of the chemical reaction is gas. And the gases are normally at very high temperatures, and the gases are normally at very high pressures, and the speed of the chemical reaction is fast. And then these gases cause some damage to the surroundings. So that's a general definition. A pyrotechnic, and you might know them as fireworks, they also are classed as an explosive, but some pyrotechnics do not produce gas. You can get gasless pyrotechnics. That's just a general definition of what an explosive actually is. So just talking about energy, how much energy does an explosive actually have? And I can compare this, say, to sugar, really. You have 5 kilos of an explosive, which is 2.5 packets of sugar. We can do the calculation. So say we have TNT, trinitrotoluene. I can calculate that how much energy 5 kilos of an explosive actually will have. And here I've told you it's 25 megajoules. That's an average value. We can convert that energy into kinetic energy using that equation, 1/2 mv squared. So if I've got the energy, if I know the mass, and here I've got 200 kilograms, I can calculate the velocity this explosive will produce. It produces gas. The velocity, it will push that projectile forward, and here I've got 500 meters per second. If all my energy, 100%, is converted into pushing this projectile forward. But explosives are very inefficient. They're rubbish at pushing things forward. And here I've got 35% efficient. So we're losing huge amounts of energy. And if you think about it, if I've got a barrel and I'm pushing the projectile through a barrel, what's happening to my energy? Well, the barrel's cold. My projectile's cold, so I'm losing energy. I've got gases going around the projectile. I've got to start pushing it, so it's friction as well. So explosives are not very good at doing this type of job. So why do we use them? What's the point when they're very inefficient? Why don't we use something else? Well, the reason we use them, the speed of the reaction is very fast. That's why your airbags in the car, what initiates an airbag is an explosive, a propellant. Because as soon as you initiate it, straight away the chemical reaction takes place and you get gases. I was involved in an accident just before Christmas, a head-on collision. I was driving, first time in my life, and the airbags came, and when I saw the airbags, and I saw this powder, yellow things, and I thought, oh, this is it. It wasn't hot, so it's a cool gas. I didn't actually know what the gas was like. It's a cool gas that comes out, but it was an explosive that saved my life, and that's what's in your airbags. Here's another video of the speed of the chemical reaction, why we use explosives. Thank Martin Baker for letting me have these videos, was that around the canopy was deck cooled, so that when that detonates, that shutters, sends a shockwave through the canopy, and that breaks it open, and obviously the pilot has propellant, which ejects the pilot out. So that's just showing you that the speed of the reaction, as soon as they need to eject, straight away these things are put in place, and explosives are used for this. So I'm looking at explosive now. I'm looking at the energy of an explosive, and I'm going to compare it to a candle. So if you take 100 grams of a candle as a stick and 100 grams of an explosive as a stick as well, you ignite the candle, and the candle will burn and give out energy. Here I've got 4,360 kilojoules. And you do an explosive, you initiate it, and you get 513. So an explosive doesn't have much energy, far less energy than a candle. And we know that. People say to me that when we have overseas, we have some legacy weapons, why can't we take the explosives out and use it for energy? Why can't we burn it and give us energy? They don't have much energy. They don't give out much energy, so they're not very good at this sort of thing. But what they're good at, if you divide the candle by how many seconds in a day, you end up with power, which is kilojoules per second. So a candle has less power than an explosive. So you're dividing the energy for the explosive by 22 times 10 to the minus 6. So the detonated explosive gives out all its energy in one go, straight away. And so it has a lot of power, but not too much energy. And that's quite important to know about explosives. So what is an explosive? Explosive has a fuel, and it has an oxidizer, which is oxygen. And for the fuel to burn, it must be able to mix with the oxygen, otherwise the chemical reaction doesn't take place. So the easiest way to mix a fuel is like hydrogen, which is a gas, and oxygen, which is a gas. If you mix those two gases together by a thing called Brownian motion, they mix beautifully, but nothing happens. I mean, we've got hydrogen and oxygen in the atmosphere, you don't get an explosion. But if you mix the two together and you initiate them with something, then you get an explosive. So this is quite important. It's the speed of the chemical reaction depends upon how well can you mix the fuel and the oxidizer together. So here's a bit of chemistry, not too much. We've got hydrogen gas mixed with oxygen gas. Now we've used that for the NASA program. And at the very beginning, they were using liquid hydrogen and liquid oxygen, and they were mixed together because you have to have cryogenics to cool these down. And when you release them, they mix as a gas. And if you initiate it correctly, it's enough energy to lift off some type of vehicle. So that's one thing, but you need cryogenics to do that. Another one, methane, which is another type of gas, and you find that in your homes. If you've got a gas cooker, when you turn your gas cooker on, what comes out is methane gas, but it's mixed with oxygen. So when you light your gas, you get quite a good flame. But what happens if you turn your gas tap on and don't do anything? Just leave it, don't initiate it. The methane gas will come out and it's quite heavy. It will go to the ground and it will mix with oxygen for the atmosphere. Nothing happens until you initiate it. If you initiate it with a spark or a match and you have enough, you will end up with a fuel-air explosion. Quite dangerous. And sometimes you see on television a gas explosion. That is a fuel-air explosion where some gas is gas leak and it's mixed with oxygen and it's caused a reaction. Methane gas, you can't smell it. They put an odour into our gas so we can smell a gas leak. So it's like a tracer. So we think, oh yeah, and it's a horrible smell too. I mean, obviously I know what the smell of gas is and you do, but it's not the gas, it's the odour that you put in the gas. So we all have a potential in our homes, if you have a gas cooker or even a boiler or a gas leak, having a fuel-air explosion. So this is another video. This is a liquid called unsymmetrical dimethylhydrazine. It's a propellant. It's a very toxic propellant. We use it in our torpedoes. It's still used a lot in our weapon systems.
That the propellants in Lance, Herfner, and UDMH are powerful enough to carry a half-ton warhead a very long distance is certainly correct. That, as with many weapons in a development stage, early tests of Lance prototypes were not always perfect, is also true. Some of these tests at the start of the program were so spectacular in their self-destruction that memory and barroom comment still lingers on. But it was precisely because of controlled test prototype flights such as these, in which not a single burn nor injury was part of the record, that Lance was to become the Army's best tested artillery weapon.
So the fuel was the hydrazine, the oxidizer was fuming nitric acid. You mix the two together. But did you see what the people were wearing at the end? They're in full PPE because the nitric acid is extremely corrosive and the hydrazine is extremely toxic. But it's effective. It works really, really well, and it's called a liquid bipropellant. And that's what we use in, well, you saw it in Lance in this video. So I'm going on now to solids. So we're mixing a fuel and oxidizer together, but these are solid now. So they don't mix like put into liquids or mix into gases. So how do we mix two solids? And this is where it gets highly dangerous because your fuel and your oxidizer separately are non-explosive. As soon as you mix them together, they become explosive. And the one I'm going to show you is gunpowder. So the way we do it, we mix them wet. We wet the gunpowder. So the fuel is carbon or charcoal in a fine, it's ground down into a fine powder. The oxidizer is what's known as potassium nitrate. It has oxygens on the molecule. And we put sulfur in gunpowder. Why do we put sulfur? And the reason we put sulfur in gunpowder is that when you heat gunpowder up, the sulfur has a low melting temperature, so it melts and it brings the fuel and the oxidizer together. So it's like an initiating or cementing agent. You can get sulfurless gunpowder, which does exist, but most gunpowder has sulfur in it. The video you're showing is gunpowder that we made in our labs, and again, we mix them wet, we grind them wet, and then when it's all mixed, we let it dry, and that's it, we don't touch them. So the first video, I'm just going to light this gunpowder, and it's in the open, and you just see how it reacts. And you can see that there's black charcoal left, so our mixing wasn't that good. So all the charcoal never reacted with all the oxidizer to give us the gases. The next one is, again, we've made it in our lab. We've taken sugar, ground it down, that's my fuel, and then we've mixed it with a weed killer, which is sodium chlorate, and that's my oxidizer, because it has the oxygens on it. And when I initiate this one, I'm adding an acid to it, concentrated sulfuric acid. And what happens is this acid starts a chemical reaction. The chemical reaction is what we call exothermic. It gives out so much heat that it causes this composition to set alight. It's what was used many, many years ago as an incendiary device. And when you burn this type of composition, the byproduct is burnt sugar. You actually smell treacle. It's really like, and when you look at it, where some of the carbon hasn't reacted from the sugar, it's burnt sugar, and that's the products. So this is another type of how we mix solids. The way we mix the sugar and the oxidizer, not that you would ever do this, so you know, you're all intelligent adults here, but you put them in a plastic bag and you shake them. And you shake them together, and that's how they mix very nicely. But of course, I trust you wouldn't do this. I haven't given you the quantities, so that's one thing. So going on then, this is a video of what they used to do in China a long time ago. They're trying to get a composition to increase our life, the life expectancy. Now, this is a chemical they're doing. They're taking honey, which is our fuel, and they're mixing it with potassium nitrate, which is our oxidizer, and they put a bit of sulfur in there, and you know why sulfur's there, and they're going to boil it up. Now, what they didn't know then, the Chinese, they didn't actually know that they were making an explosive. They didn't know that. They're trying to actually increase our life. So have a look at this video.
That jar would get us something interesting happening if we got about the same quantity of the other two ingredients, the saltpeter and the sulfur. That should go nicely.
Why did they ever think of mixing these things together at this point?
The idea is to try to subdue the fiery properties of the sulfur and of the saltpeter so that they will be suitable for taking as a medicine, hopefully an elixir of life.
Oh, I see. So, ironically, in trying to find a means to eternal life, the Chinese alchemists found a substance that could kill. I've never done any alchemy before. This is my first venture into the world of alchemy.
If you make a success of it, it's a new career, really, isn't it?
Potentially lucrative, I think.
Yes, indeed, indeed. Now, that looks pretty well stirred to me. I would think now if you start cooking that, that will finish the mixing.
Despite being earlier than the incendiary powder of 1044, the chemistry of this mixture has the potential to be more explosive. So, because of the water in the honey, that is dissolving the saltpeter,
yes,
and then allowing that to carefully coat all the bits of
all
sulfur.
the particles of carbon and sulfur will now be very, very close to molecules of saltpeter, which, when they get hot enough, will start releasing their oxygen just right up close to them.
I think that's going to go in a sec.
There's little puffs there, exciting little puffs, I say. We slightly move ourselves out of the immediate line of that, that's it.
Whoa! Okay. Wow.
That was quite striking.
Wow.
Yes. Well, as the Chinese alchemist said, don't try this at home.
So, incendiary mixtures were being explored by the Chinese alchemists as early as the mid-9th century. From the 12th century, as China was swept by waves of war with neighbouring peoples, they started to use their fast-burning powder.
They put it together and they went outside in a big pot and they put it on a fire and they decided to heat it up, and it was bubbling and bubbling and bubbling, and then eventually it got to a critical temperature where the chemical reaction took place and the whole thing just shot out the pot and just went everywhere. It didn't explode, it actually produced this gas and it just lifted all this boiling hot honey out of the pot. So it actually did become like a propellant, really, and that's what happened. Carrying on from there, just a bit of history, that the explosives were supposed to be used, we think, by obviously the Chinese, and they were using it as fireworks. So that we don't know the first recording, but in 700 AD, that's when we saw a bit about the fireworks and looking at the formulations that the Chinese were actually used. It never came to Europe until about the 13th century by Roger Bacon, and they say that those, you know, sort of friars, they were the scholars, they used to make alcohol, and they used to make explosives. So he was the first one started to tamper with it, but we weren't using it for entertainment. We were at war with everyone, so that they were making Greek fire and throwing it over the fortification of the castle. So that, unfortunately, we were always at war with each other, so that's why we were making this gunpowder. And then it was all made by hand, obviously quite dangerous. And then in the 15th century, in this country, a place called Waltham Abbey, which is closed now, but it used to be like a royal ordnance, the MOD used to own it, and that's north of London. What they did, they discovered these big wheels that they used to rotate, and they used to grind the gunpowder down. So now you've got a reproductive manufacturing process where it's reproducible. So the gunpowder was always the same that comes out, and it was called corned gunpowder. And if you have the opportunity to go to Waltham Abbey today, they tried to sell off the site to build houses on, but the land was so contaminated they couldn't. So there's a museum there, and you will see these wheels. Sometimes they have displays, and say that's at Waltham Abbey. So that was in the 15th century, and the formulation of gunpowder really hasn't changed since then. And we still use gunpowder today, mostly in fireworks, because it's, unfortunately, gunpowder, when it gets wet, it doesn't actually work very well. But say it does still exist, and a lot of these people do these reenacting, often use gunpowder. I don't know which one that is blowing up, but often people have pictures of things blowing up. I have to tell you a story. I don't know how much time I've got here, but Queen Victoria, when she was in the Tower of London, along the Thames was coming a barge, and it had some gunpowder, but it also had it separate and didn't have electricity, so they had their little lamps on the barge. Well, this barge set on fire, and there was a massive explosion just outside the Tower of London. And so all the windows, I don't know, windows went in or they smashed, but she heard this explosion, and she said, enough. I've had enough of people tampering with explosives. And she started the Explosive Act. So the Explosive Act was made by Queen Victoria when she heard that first explosion. Because before then, anybody could make explosives. It was, it's quite possible to get hold of material. There's no problem. So it's down to Queen Victoria that said, right, we have to start limiting what people can do. So this is another video. Keep our fingers crossed. This is where, instead of taking gunpowder in the open, if we put gunpowder and enclose it and trap the gases or direct the gases, we can use it sort of in a weaponry. So this is what this video is about.
Confining gunpowder changes the speed of the reaction. It goes from something that just burns into something that really explodes. Gunpowder doesn't need air in order to burn. It gets all the oxygen required from the crystals of saltpeter, potassium nitrate, that are in there, which means it'll still burn in a confined space. And putting it in a confined space increases the rate of reaction. Drop it in here. So I'm going to wrap it up. When it's confined like this, all those grains, the carbon, the sulfur, and the potassium nitrate, are all physically much closer together, which means the reaction can happen more quickly. And as the reaction happens more quickly, more heat's created, making the reaction go even faster, and it's a runaway process. With gas being produced so quickly and heat making it expand, there's the potential for explosive force, if I can channel it like the Chinese did. This is my first attempt at a cannon. I've decided to build it out of clear acrylic so that we get to see what happens inside a cannon. Now, I'll drop that on there. Oh, it fits in nicely. My cannonball. So there it is. There's going to be an explosion in there. That explosion will produce hot, expanding gas. There will be a big pressure rise in that part of the chamber. That pressure will exert a force all around the container, but these three sides should stay where they are. This fourth side here, where the tennis ball is, won't stay where it is, and that tennis ball will leave at an undetermined speed that I suspect will be pretty quick. Let's find out. Three, two, one. Yeah, that worked like a cannon should work. Wow. You can see how the gunpowder produces hot gases at just the right rate to push the ball out. This technology quickly spread west, through the Middle East, and by the 14th century, the Europeans had rockets and guns too. But something...
Okay, so that's gunpowder when we confine it, and all it's doing is producing a lot of pressure. The white thing you saw was just hot gases radiating white light. So carrying on from there, instead of mixing a fuel and an oxidizer together, we can move on and make a molecular explosive. So this time, we're taking a molecule, we're synthesizing a molecule that contains a fuel and the oxidizer on the same molecule. So you've got your carbon and your oxygen chemically linked together. So no mixing, we're actually synthesizing a molecule which is an explosive. An example here is toluene, which is, for non-chemists, the grey bits are carbon, and then you've got your hydrogen sticking off. It's like a benzene ring with a methyl group sticking out. If you mix that toluene and you mix with nitric acid, you need a bit of sulfuric acid as well, just leave it, and you end up nitrating it. So you end up with 3 nitration groups, which are NO2, and you end up with trinitrotoluene, TNT. So I've gone from an inert type of material to an explosive material simply by nitrating it, by doing those, putting that NO2 onto it, and you get water being given out. So here's another one. This is nitroglycerine. So you can see my carbon and my hydrogen, which is my fuel, chemically linked to my oxygen. And there's my NO2, my nitration groups. Now you might wonder why. Why is there a nitrogen there? She hasn't mentioned anything about nitrogen. What's that got to do with an explosive? Well, if there wasn't a nitrogen there, if it was just OH rather than NO2, which will be glycerine, that doesn't explode. By putting an NO2, the bond between the N and the oxygen is very weak. Oxygen is slightly more negative than nitrogen. The bond holding together is what we call a covalent bond, but it's a very weak bond. So you're adding a weak link to the molecule. So when you initiate the molecule, the first thing that comes off are the oxygens linked to the nitrogens. So it starts a chemical reaction. As soon as you get that chemical reaction starting, then the rest of the molecule breaks apart. If you didn't have that nitrogen there, it wouldn't be an explosive. So by nitrating something, you're making it more energetic because you're adding a weak link to it. That's the majority of organic type explosives. They will be nitrated. So this is nitroglycerin. Can you see the man? He sits on a stool with a one leg. When they made nitroglycerin, it was so dangerous that if he fell asleep, it would fall off the stool. So that kept him awake. So he's always a one leg on the stool, because it was very dangerous. And it still is very dangerous to make. We haven't improved the manufacture of nitroglycerine at all. This is another video. This is where I work now. This gentleman, James, came to us, and this is a colleague of mine. He's making nitroglycerine in the lab.
The middle of the 19th century provided a turning point in the story of explosives. I've had to come here to the Defence Academy of the UK because we're going to make what they first discovered in 1846. An Italian chemist, Ascanio Sobrero, reacted nitric acid with glycerine. Dr. Alex Contini is one of the few chemists experienced enough to attempt this process.
7 and rising.
Each time the glycerine is added to the concentrated acids, he has to stir it and make sure it stays cool. Every degree of temperature rise makes a premature explosion more likely.
10 and rising.
looks fairly innocuous, but Sobrero discovered it has some pretty surprising properties. And we're only going to use the tiniest amount to show them. Sobrero wrote that the safest way to demonstrate these properties was to dip a hot wire into a glass bowl of the substance. But he was scarred for life by flying glass, so we are going to try something different. Even slowed down more than 500 times, the explosion is incredibly fast. That's a bit of a kick. Now, the reason why that's so sharp is because if you look there, every single molecule of that liquid has disappeared. It's turned almost instantaneously into gas, hence the nice explosion. But something new here is happening. That's not just fast burning, it's something completely different. It's something called detonation.
Okay, so what's detonation? When Alex hit the nitroglycerine, as he impacted it with a hammer, he squashed it. And as he squashed it, all the air pockets inside that liquid were being squashed, and the temperature of the air pockets rose because as you squash something, you're increasing the pressure, you're decreasing the volume, so the temperature goes up. If the temperature goes up to above the ignition temperature, the nitroglycerine would ignite. But what happened is the speed of burning became supersonic. So when the speed of burning becomes greater than the speed of sound within that liquid, you get detonation. So it's like when Concorde just go for the sound barrier, you hear boom, it's exactly the same. So as it goes through the sound barrier, it turns into a shock wave. So detonation is a shock wave, and it's supersonic. Supersonic, it's not the speed of sound through air, it's the speed of sound through that liquid. So that's what detonation is, simple detonation, and I'll show you some more detonations, but that's in nitroglycerine. So this is another one. This is cellulose, which is cotton wool. If you take, or sawdust, if you take cellulose, and that's what it looks like, and I put it in nitric acid and fuming nitric acid and sulfuric acid, and leave it there, you nitrate it. So the OH groups, you can see, become NO2 groups. And you know now, if you nitrate something, I'm adding my weak link. And so I end up with what's known as nitrocellulose, or I think what they call it now, gun cotton? Yeah, gun cotton. But that is an explosive. So simply by nitrating it. And this is me many, many years ago. I was making this, and you'll see what happens when you burn nitrocellulose in the open atmosphere. The second video I'll talk about in a minute, but we're going to burn nitrocellulose inside a rock.
As it's known. I mean, now we've washed the acid off and dried it. It feels exactly like cotton wool, just like we started with.
The only difference with this one compared to the cotton wool is that we've got the oxygen actually linked to the fuel.
So because we've changed every single molecule of the cotton to gun cotton, then it's going to go exactly the same every time.
Yes.
Go on then.
Right, are you ready?
I'm more than a little intrigued.
Okay. Stand back.
I am already.
Ready?
Ooh. That gives off a lot of heat.
Heat, light, lots of gas being given out, and then you can just have a look, and there's sort of black bits there, that's a carbon, so it hasn't fully oxidized.
Right, so there's not enough oxygen for all the carbon that's in the molecule, so we're just left with some carbon.
That's right.
And that's just a very, very rapid burn, that woof. Like with the gunpowder, when you just set it fire, it's unconfined, so you don't get an explosion, you just get this rapid burning.
It all goes up into the atmosphere, and it's all disappeared as gas. Okay, so that's nitrocellulose in the open. The next video is what they've done. They're going to take some gunpowder and put it into rock, and then that will simply produce gas, and it break the rock open. If you put nitrocellulose into a rock, you trap the gases, and what happens is, as the nitrocellulose is burning, the pressure can't escape, so the speed of burn gets faster and faster and faster, and then it becomes supersonic, and then you get detonation. And so what happens is, as a shock wave goes through the rock, it shatters the rock completely. So rather than just gases breaking the rock, you've got shock wave, and it's completely different. And that's what you'll see in this second video.
Amount of gun cotton. So innocent did the gun cotton look that one man said he would sit on the hole in return for a drink at the local pub. Luckily, he was persuaded to watch the test before committing himself to the bargain. First, 30 grams of gunpowder. Let's see if it's more successful than in the mine. Well, the rock split, but not at the hole where the explosives were. It looks like that explosion there maybe sent some kind of shock through the rock, and it's peeled off here where possibly there was some sort of fault line. Now we'll try just 5 grams of gun cotton, looking like it couldn't possibly do much damage. That's a completely different story. In slow motion, you can clearly see all the gases the explosion creates. Brown nitric oxide, steam and others splitting the rock apart. It's just astonishing. A couple of 100 kilos of rock has practically disappeared. There's some fragments over there, bits down here, and look at that. Where it was actually placed, there's nothing at all. Like that. Look down here. That's the hole where it's packed in. So this was the other way up. You can see where the clay was. You can see all the way down here, and it's just split it. Now, this is gun cotton, and what's happened here is when the gun cotton has been compacted, confined in there, it's detonated, which is a
Okay, so that you can see by actually trapping the gases, the pressure, you can get detonation. The next video you're seeing detonation now. This is what's called det-cooled. It's got another explosive in it, but you just see how fast a detonation shockwave goes. You're talking about 5,000 to 6,000 meters per second.
Watch this. This is detonating cord. It's a spun cord with a line of high explosive right down the center of it. When it's detonated at one end, the wavefront moves extremely quickly right down its length. Slowing the process down 250 times, you can see the detonation traveling at about 6 kilometers a second. When the force of the detonation wave hits the surrounding air, it creates a supersonic shock wave. You can see the shock wave distort the air like a bubble coming out around this modern high explosive. Shock waves and reaction speeds like this were a phenomenon that nobody had come across before, and it made these new high explosives very powerful and potentially very...
Okay, so that's just showing you what detonation looks like and the speed at which it goes. So these are some other types of molecules. This is RDX, cyclotrimethylene trinitramine. Don't worry too much about it, but more importantly, why is it called RDX? The reason it's called, that's a common name for it, is when the researchers before World War II were researching into a new explosive, they didn't want the Germans and other people to know what we're doing. It's all hush-hush at Waltham Abbey, so they called it Research Development X. And we stuck with it, RDX, and that's what we call it. And then there's another molecule, HMX, higher melting X. Again, we thought we were quite clever, but obviously the Germans and others were doing exactly the same thing, but we wanted to keep it a secret, and we kept the same name. So these are two very common explosives. This is another one, CL-20, China Lake 20, developed by the Americans. It's a cage structure. You see the structures are quite bigger now, and that is probably the most powerful explosive we have today that's manufactured. Quite difficult to use because it's quite dodgy to handle. It's quite sensitive to handle. But again, the explosives are getting bigger and bigger and bigger. The modelers are modelling loads of things for us, but you've got to be able to make it. And we're experimentalists. So not only make it, then and how dangerous is it to make? But this is one that's actually being made. So, just carrying on, you've got, that was an explosion. This is a propellant, this is rocket propellant, and it's just showing you that if we put propellant inside this type of missile, we can control the gases to lift something off. So this is rocket propellant, rather than in a gun barrel. And these are called deflagrating explosives. They burn, but deflagration means that they burn at a high rate. But no detonation is below the speed of sound. So they're subsonic. Okay, the next one is countermeasures. And you'll see these are pyrotechnics now. And this is just showing you some countermeasures. And these are very clever, these pyrotechnics. They will burn and give, and what they do, they burn in the same wavelength as the aircraft. So it's very clever how they make them. But that's the counter. It's actually getting rid of them at that time. So, primary and secondary explosives. We have explosives, and we can divide them. Besides propellant pyrotechnics, the explosives are divided into primary and secondary. Primary are really sensitive to handle. We don't like to have much of them around, whereas secondary are less sensitive. This video is in our lab, and at the bottom of that yellow cord is lead azide. It burns to detonation. And you see me light the top of it, and down the bottom of this cord is a spark, and that will ignite lead azide. It burns to detonation, it will detonate, and the shockwave goes into the glass test tube and shatters it, completely destroys the glass test tube. And the graph on your right-hand side just shows you, this is like an activation energy curve, is that you have to put energy in, E, to get the reaction starting, and then it gives out energy Q, a lot of energy. Little energy in, lots of energy out. If E is very small, that means you only touch it or just light it and it goes. They're primary explosives. So primary explosives have a small E. If E is very large, you kick it, push it, pull it, it doesn't go. That's a secondary explosive. So there's a difference. So we can classify explosives by the activation energy, very sensitive or less sensitive. So this is the future now. I'm mindful of the time. So this is what we're looking at nowadays. Nano explosives. The reason we like nano is that they compact very well, and mechanically they are very strong. So we might have caseless charges if we can do nano explosives. So a lot of work is being done on nano explosives. Another area is looking at co-crystallization. Instead of making a new explosive, why can't we take two explosives existing, one that's very has lots of high detonation pressure, another one which is very safe to handle, mix the crystals together and recrystallize them to create a new crystal, and that's called co-crystallization. Not very easy to do. We're doing a lot of work in this area. When we mix them, sometimes we get the crystals just come out together. But that's another way of doing it, is make a new explosive from existing ones, and that's called co-crystallization. Another area is this country does not manufacture explosives. We haven't done this since 2005. And now with hostile states and things in this world, what's going on, we want to start to manufacture explosives again. So what we're doing, instead of doing it in big pots, we're saying, okay, if we're going to start from zero, let's think of new ways of doing it. One way to synthesize a new explosive is have what's called flow nitration. You put all your raw ingredients at one end, and then the chemical reaction takes place in a tiny, tiny microreactor, and you take away the explosive. So if there's initiation, it only occurs in that small microreactor, so it's not so dangerous. In the past, we've done it in big pots. You know, just chuck it in and stir it, and when it goes off, you know, it's a huge accident. So microflow reactors are the future. And you can have lots of them, don't need to have one, lots of them, 24 hours. It's safer to use, so a lot of research is being done in this technology. Another one is on mixers. Once you made your explosive, you have to mix it with other ingredients, because explosives look like sugar. So we're looking at various types of mixers, and you've got ones that go like this and ones that go like that. But the most important one is on your top right. It shakes it, and it's called a resonant acoustic mixer. Doesn't stir it, and you can put a pot on, and you put a pot full of pyrotechnics, stick it on, it shakes it, and it mixes it. And you take that off and put another pot on with an explosive. So you can put different ingredients, or you can have lots of pots all shaking at the same time. So there's no contamination, no cleaning. It's very, very good. And so again, this is the way of the future, is resonant acoustic mixing, shaking it to mix it. And a lot of work's being done in this area, and we've got the bench top. We've got, where I work, we've got the bench and we've got the 5 kilos. We're scaling up now, but they got bigger, and they use this a lot in pharmaceutical and other industries, and we're trying to use it in explosives, and we're trying to see, you know, let's say how, no, where I work, we try to get it to blow up, because we want to see, let's see the limitations of it, and we couldn't do it. We left it for, put ingredients, left it for 24 hours, did various things to it. And I say it's quite safe. There was an explosion recently, but not where we work, so we're trying to find out why. But no one was hurt. It was research, and that's what research's for. It wasn't in production. So the most important thing is, why did it go up? And we can learn from it. So that's research. Another area is laser ignition. Is why do we light explosives with electrical currents? Why can't we use a fibre optic? And why can't we excite the molecules in explosive with laser light, get them to excite and then get them to burn, putting energy in? And you can have one laser with lots of fibres and detonating all over the place. That's another area, laser initiation of explosives. Take away the wire, take away the current, take away the electromagnetic radiation that we're surrounded by. This is another big area looking at initiation. 3D printing. So all these are where I work. We're doing all the research in all these areas. Let's 3D print an explosive, and we've done it. We 3D printed a pyrotechnic. We 3D printed a high explosive. So it can be done. And the good thing about 3D printing is that if you go to a theatre or somewhere and you want to print a certain type of explosive, you can do it there, straight away. So you take all the raw ingredients with you, which are inert, and then when you 3D print it, that's when it becomes dangerous. It's not too bad, actually. So you can 3D print an explosive. All we've done so far is a composition. We haven't done a detonator yet. I'm sure that's the future. We've just done the composition and then seeing if it actually works, and it does. So that's the future, is 3D printing. Another one, and this is really, this is way, way ahead now. Why cellulose, for instance, we buy our cellulose from China and other countries. We're having a problem with supply at the moment. So in this country, we're saying, okay, we're growing cellulose. And we found some bacteria that if you stress the bacteria, it protects itself with like a little shield. And this shield is cellulose. So we're taking the cellulose, grinding it down. I'm not doing it. This is at other universities who are clever at this. We get the cellulose, and I'm nitrating it, and I'm making it into explosive. So the future now is moving away from supply overseas and thinking smartly about how can we use biology or other types of synthetic chemistry to manufacture our raw materials rather than the way we've been doing it in the past. So this is very, very, so we've been working on this 1 year, it's working, we've made an explosive, and then we're going to, they're DNA profiling the bacteria, they're going to genetically modify it, way cleverer than I am. So they're doing all that, and then we'll do the explosive. So that's something for the future that's going on, and many other research in this area for the raw materials. Coming to an end, there are questions. So just more importantly than the book, this is a 4th edition. If you are, like me, mad, pyromaniac, love chemistry, this is it. But more importantly, this country never used to run conferences and explosives. This is the second one this country has ever run, and it's going to be in Edinburgh. It's this year, and it's going to be in June in Edinburgh, at the University of Edinburgh. And we're looking at artificial intelligence, we're looking at machine learning, we're looking at robotics, because this is a future. You know, how can we use this? Computer modelling, simulation, novel explosives. So this is the next generation, and this is at this conference. So it's all what the future is, and we're doing space as well. We've actually invited some people from the space industry, and they're going to come. So we're looking at space, how we can develop new explosives for the space industry. Right, I have to stop there. Sorry, just keep going on. And, but thank you very much. I know there's question time. I'll go and sit over there, and hopefully you know a bit more than you did before you came. Right.
So I'm sure there'll be several questions. Could I ask you to just raise a hand, and so the microphone will appear.
Not too difficult, please. Oh, I've stunned them all.
Yeah.
Oh, there we go.
So obviously you've got different types of explosives for whether it's a propellant or the detonation for military purposes, if you will. But for a rocket, which fuel gives the best bang for its weight? So, you know, what's your best return of energy for rocket fuel?
So a lot of research has been done in this, and the theory is that the bigger the molecule, the more nitrogen we can get on the molecule, the more gases we can be given out. But more importantly, for the future, it's got to be green. It's got to be environmentally friendly. So we're looking at now propellant, rather than giving off toxic gases, which propellant does give off, like hydrochloric acid and other things, not good for us, the way of the future is looking at propellant that is environmentally friendly, better starting materials that are not toxic, and producing more of the nitrogen gas rather than the NOx gas, which is NOx, which is not very good for it. It's a brown gas. So that's the way, the future. Lots of nitrogen, big molecules of nitrogen, but producing friendly gas. Hope that answers your question.
Thank you, very interesting. I work in planetary science and I understand there are some new propellants being developed which are much safer for basically manoeuvring satellites. Can you comment on them?
Okay. My comment's very limited because we've never been involved and no one's ever asked us in this area. We'd love to get involved. And so I can't comment too much because all I'm aware is that there are, as I said before, there are propellants that have been made, and we haven't been involved in the research. We can, because we have ideas, but my understanding is that they are environmentally green propellants, but I don't know too much about that. But I'd love to be involved, and we've always said, come to us because we have so much knowledge for this country, but you buy it overseas. At the moment, it's all overseas because we don't manufacture. So we'd love to manufacture, well, not us, but help to manufacture these in this country and don't bring them from overseas.
You mentioned explosives for use in space. What characteristics might be desired for that?
Well, the only explosives that, okay, you get the propellants, of course, are the ones that they think. There are other ones that we have to use, which is we can use propellants not only to lift things, but to push things forward. Like if you need to cut a metal, that can be a propellant which will push something forward, which will cut through a metal, or you can use propellants for shutting down things as well. So a lot of them, they're called squibs or actuators, and they will have propellants in to move things, like the satellites, move things around, and say the propellants for the missiles. And I think other types, pyrotechnics, if you need to give out some type of colour, and also for defence, countermeasures, but that's way. I mean, if you don't want people to see your satellites and things, obviously, but I mean, I'm sure people work, we're not, but I'm sure people are thinking about that, the countermeasures, of course, as well. But that's, say, the space industry is one of those things that we keep looking at, and we would like to explore a bit more, but the space industry seems to me to be a very closed shop at the moment, but it's interesting.
Thank you very much. One of the questions I have is that I was in correspondence with a boat builder that was using small-scale explosives to mould large aluminium and non-ferrous metallic objects. Would one of the objects of non-toxic detonations and small-scale events like this be used in forming metal panels without the need for dangerous, noisy presses, but also be able to develop detail at the crystalline level? So let's say you could form railway lines out of it using explosive. I spoke to a man called Stephen Pollard who was using explosive detonations for aluminium hulls into a former, but he said that it could also be, if you had smaller scale systems on like a charge, you could then get the detail out of it.
Oh, yes, to your question. We do, it's a pyrotechnic is what you're using, and pyrotechnics will burn at very high temperatures, and if you can get it right, use it for welding or heating up materials, you can actually do it. It depends upon the metal, because if it's too hot you might oxidize metal, so it's a fine line between too hot and actually getting the joints together. I can say that probably it doesn't exist today to do it, but certainly it can, I think with a bit of research, I think by my colleagues who's a pyrotechnic expert in this, I think with a bit of research probably you could identify something, because I know they exist, and we often use them to melt things for our practicals, and they are pyrotechnics, and it's a simple chemical reaction, and actually when you watch it shoots down these hot molten products, and it will melt things, absolutely. And you can even melt a metal, because it's 3,000 to 4,000 degrees centigrade. But I think a bit of work needs to be done on that, actually.
You mentioned that you're using the systems for pharmaceutical manufacture. Is that just nitroglycerin, or is there other things that need to be made that way?
Okay, let me just go back. We don't use it. The mixers are used in the pharmaceutical, and they already exist. And so we're looking at them, and we want to use the same sort of technology as they're using. Just to go answer a bit more on your question, nitroglycerin is used in the pharmaceutical industry because it thins blood. So if any of you have had a stroke and you spray something under your tongue, that is actually nitroglycerin. But they don't call it that. It's got a different name. I've forgotten what they call it now, but a slightly different name. But it's a very, although it's low concentration, it is used. And it's very good for you, nitroglycerin, because it thins your blood, and it's quite healthy for you. And actually a lot of the explosives in the 19th century initially were made for their medical, not for explosives. And in small quantities, they're very good for your explosives, small quantities. They were, but yes, but we are using technologies very similar to pharmaceuticals.
I think there may have been a question at the back, right
there. There's a young lady here. Oh, and one over there.
Hi, thank you. I was wondering if you could speak more to how 3D printing is being used for explosives, so specifically like what sort of types and how it's...
I sort of can. There's patterns on it, of course, but you get ones that 3D printing which are like inkjets, so they're like rheological, they're like liquids that come out. The ones that we're doing is slightly different, so we use a powder bed, and then what we do, you have your raw ingredients at the top, and then what we tend to do is you put your explosive as a powder, and then you put your, normally a polymer on it, and then you'll cure it, and then it goes solid. And then we do it layer by layer by layer. So it's a very thin layer as we build up. So it's your explosives, generally with a polymer, with a curing. So we do it differently, but others have actually done it with like a liquid, and then so the whole thing's in one go, and put it down and then cure it. So, but there's different types of 3D printing, and we're just trying to mimic what's out there. But our one is a new one, and we did it with Southampton University, and so the pattern's actually going through at the moment on ones that we're developing, but it's a dry bed. That's what we're using.
Yeah, thank you for your speech so far. I was also going to ask about the 3D printing.
Right.
I'm aware involved with the exploitation of the RAM. Where does the 3D printing process sit in terms of exploitability? Is it just in the lab at the moment, or?
Yes. We're not the only ones doing it. There's other defence organisations doing 3D printing. I think, yes, it's not being used, it's on the research stage. The problem is with 3D printing is the density. And it's getting the density high enough, because in explosive, the higher the density, the higher the velocity of detonation, the pressure. So it's getting that density up. So at the moment, we know it works. It's just a question now, is it good enough? And we're doing quite small. And so, but yes, it's not at the exploitation stage, but it will be. I mean, more work needs to be done on it. And certainly is for the future. But at the moment, it's not quite there yet. But
any indications of what timescales?
Well, I can say the MOD Defence are putting an awful lot of money for the next few years into new technologies, because we're trying to speed things up. Yep. So I think I would say probably 4 to 5 years, we should be much better for exploitation. At the moment, too new. But give us 4 or 5 years, we'll be ready, I should think.
Thank you.
Pleasure.
I think we have time for one more.
Thanks very much. I wonder if there's any development in the for shaped charges with the composition for that in the development.
Not much to. And shaped charges, for those who don't know what we're talking about here, shaped charges is it's like a cone, a metal cone, and you surround it with an explosive. And when the explosive explodes, it melts the metal and it shoots out a slug, and it becomes a penetrating charge. So it goes through metal. That's a shaped charge. So it's not the explosive doing anything, it's the metal that melts and it shoots it forward. I can say no. Most of the composition of shaped charges are normal, the RDX ones. Nothing much on that actually has changed on shaped charges. It works and it's cheap to make. Yeah. And so, no, I can't think of any new developments in that area.
No, I guess it's fairly mature anyhow, isn't it? So maybe you don't need to. Thanks very much.
My pleasure.
Okay, thank you. So I'd like to thank Professor Akhavan.
My pleasure. My pleasure. Thank you.
If we could